The purpose of this video is to explain something about electronics, but also to explain about how I built this little amplifier box. But first I should explain the why I built the amplifier box. I have a software-defined radio. From this picture it is hard to tell what size it is, so I'll put some dimensions on it. What a software-defined radio is basically a radio that covers a very wide band of frequencies. It encompasses the normal AM radio frequencies, FM radio, the weather band, shortwave radio, the amateur ham radio broadcasts, and all the way up past the frequencies the television stations use, but it can't decode those signals. The SDR does an excellent job of picking up AM and FM radio stations because those are very strong. But the shortwave stations and amateur radio stations are very weak. With the not very good antenna I have, I pretty much can't pick them up. Before we start designing an amplifier, it is good to set down some specifications for it. I carefully measured the impedance of a piece of wire stapled to the vines, found that it was about 300 ohms, and this is the impedance that we need to match to. The specifications for the SDR say that its input impedance is about 50 ohms, and matching this low impedance to the much higher impedance of the antenna is the main purpose for this amplifier. I decided I also wanted to increase the signal voltage by a factor of something more than 1 but less than 10. I also want this thing to have a power on LED and to be small in size. At this point we need to go on a little bit of a side quest because I realize that I'm about to use a number and some folks may ask what UFO I flew that number in on. We have all seen graphs of current versus voltage for diodes that look like this with this equation. I draw your attention to the fact that the larger the current that is already flowing, the greater the change in current that will be caused by a small change in voltage. This appears like there is a resistance which has a decreasing value for increasing levels of current. Folks who like math will note that this is an exponential function, and the derivative of an exponential function is itself an exponential function. Please remember this later when I'm talking about a diode and suddenly a number 25 millivolts appears. This is the schematic for the amplifier I decided to build. I will now take you through the design, doing a little math, but not too much. I opted to use a red LED because a red LED has a forward voltage of about 1.5 volts. We can assume there is no voltage drop on R6, so the base is at the same voltage as the LED. This puts about 1 volt on the emitter of our transistor. I decided I wanted about 2 milliamps flowing in the transistor. With a bit of Ohm's law, that comes out to about 500 ohms, but in my collection of parts, 470 ohms was the closest I had, so that's the resistor I used. I assume you remember our little side quest about the current flowing in a diode. Here we come back to it again. We have 2 milliamps flowing into the emitter of this transistor, which is 2 milliamps flowing in a diode. If we ask Mr. Ohm's opinion about 25 millivolts and 2 milliamps, we get a resistance of just about 12 ohms. for small changes in the voltage. R5 and C2 put something like 3 ohms in series with the 12 ohms that we just calculated. So we can say the emitter of the transistor has a resistance of about 15 ohms for small changes in the voltage. Almost all of the current that goes in the emitter of the transistor goes out on its collector. I use some copper-clad circuit board material as a base to build the circuit on. I temporarily soldered the LED onto the amplifier, but it will be moved later when I put it in a box. To control the software-defined radio, I use a program called GQRX. At least I think that's how you're supposed to pronounce it. To be able to receive this 10 megahertz and also to turn on the amplifier, I had to change a couple of settings to do with what they refer to as the I/O device. It not only plays the sound out the speakers, but it also gives a spectrum of the amplitude versus frequency of the received signal. This bit down here gives the scrolling version of the spectrum, where brighter colors mean a stronger signal. With this all set up, I only need to wait till well after dark, till the effects of the sun stirring up the atmosphere have faded away, and then I can start to receive a station called WWV, which sounds like this.
At the tone, 15 hours, 0 minutes, Coordinated Universal Time. National Institute of Standards and Technology time. This is radio station WWB, Fort Collins, Colorado, broadcasting on internationally allocated standard carrier frequencies of 2.5, 5, 10, 15, and 20 megahertz, providing time of day,
I found this nice little plastic box. It is nice because the inside surface of the lid is nice and flat and smooth. With a little quick machining, I can now mount all the stuff to it, complete with some double-sided tape to hold down the circuit board. I could then stick down the circuit board like this. Then I can wire it up. Oh, rusty cowbells. I flipped the RF connector and the LED around. Oh well, I can just have the wires go over each other. Now I just need to snap the box together. Now that it's in the box, it's time to give it a good thorough testing. So I set it up and waited until quite late at night to dial around and see what shortwave stations I could get. Oh drat, there's a problem. No matter where I dial, I can still hear one of the local AM talk radio stations coming in. Obviously, the amplifier is amplifying that station up to so strong of a signal that it's overloading the input of the SDR. I'm fixing this like this. Making that capacitor smaller reduces the gain for all frequencies below about 10 megahertz, like this. I think it will be okay because there will still be a gain of 1 at 3 megahertz, and we are still getting the conversion from the high impedance input down to the 50 ohm nominal impedance output. The following night, I stayed up late again and put this to the test. Tuning to 3.889 megahertz, I could hear some amateur radio folks, also known as hams, chatting away using lower sideband modulation. There were several stations with people talking in languages I don't understand, and at 4.84 megahertz some music was being played. So it appears that down near the 3 megahertz range this is working. Up at 15.11 megahertz I could hear some Australians discussing some sheep and some kangaroos getting in with them and something about diseases. I came in part way through, so I don't know what the discussion really was about. I think I should finish by drawing some conclusions. Although this amplifier can help, it is really no substitute for having a good antenna. It does take a lot longer to do stuff while making a video about it, but I think that this is the sort of project that could be done in a few weekends. I did end up with one passable amplifier circuit and 0 burnt fingers. My video of the flying saucer came out far better than I could have hoped for. If you found this video interesting, entertaining, useful, or even if you really hated it, kindly leave a like and put a comment below. Thanks.